Welcome friends, myself Rahul Thakkar from LJ Institutes of Engineering and Technology. Now, in the current video, we are covering the topics such as ruby lasers. Okay, so let us start with the first topic of today's session, that is ruby lasers, or also we can say that solid state lasers. So ruby laser is the first successful developed laser in the year 1960 by Maiman, M-A-I-M-A-N. That is the name of the inventor. Ruby is a crystal of Al2O3 in which a few aluminium atoms are replaced by chromium atoms. The chromium atoms have a metastable state which are used for lasing action. So in Al2O3, few atoms of Al2O3 are replaced by chromium. Okay? Now the construction of ruby laser is as follows. You can see in the figure, the end faces of a ruby rod in the form of a cylinder are polished, flat and parallel. One end of the face is completely silvered and other is partially silvered. So thereby they provide an optical resonator. Okay, one is completely 100% silver, means a perfect reflector. One is partial reflector. So a pair of perfect reflector and partial reflector creates an optical resonator. Okay. The ruby rod is surrounded by a helical xenon flash tube. As shown in the figure, you can see a xenon flash tube is surrounded, which provides an optical pumping. The ruby rod is placed in a glass tube through which a liquid nitrogen is circulated for cooling, as a very large amount of heat is produced. In such a kind of system, a very large amount of heat will be generated because of that interaction of electrons. So for cooling, a liquid nitrogen is circulated surrounding. Okay. Now let us move on to the working. An intense flash of light is produced by a xenon flash tube. The chromium atom in a ground state absorbs this light in the wavelength range of about 5500 angstrom, 5500 angstrom, and are raised to a wide band of energy level. Okay, as you can see in the figure, the energy level band is shown at the below. The mean life of atom in this state is very small, of about order of 10 raised to minus 8 seconds, and some atom from this energy band jumps back to the ground state, whereas some drops to the intermediate metastable state from E3 to E4. Some atoms come from E3 to E1 again back, and some goes from E3 to E4. A very intense flash from the xenon tube produces a population inversion in this state, where the mean lifetime is few milliseconds. The transition of atom from E2 to E3 and E4 is a non-radiative, and this crystal is converted into a vibrational energy to the atoms in a crystal. Some atoms in the state E3 emits photon spontaneously by falling to the ground state. Some of these photons, which travel along the axis of resonant cavity, produces stimulated emission, due to which the intensity of light builds up along the axis of cavity. The laser is transmitted through the partially silvered surface. Each flash of the light from the xenon lamp is used to produce a pulse of laser. Hence, the ruby laser is pulsed laser. The ruby laser is a high powerful pulse laser in the visible range, but the efficiency of laser is very low. Okay. So that is one advantage, that is highly powerful, but on the other hand it has some disadvantage, that its efficiency is very low.
Now, the next topic is Nda laser. This is a 4-level solid-state laser system in which yttrium aluminum garnet, that is Y3Al5O12, it's a chemical compound which is commonly called as YAG, is doped with neodymium ions Nd3+, and it is the active medium. As you can see in the figure, there is a xenon or krypton flash tube. The power supply system is attached in a circuit diagram. Okay. Now, over here is an ellipsoidal reflector in which a xenon flash lamp and laser rod are kept. This is a 4-level solid state laser, as I have told you earlier. Okay. Now, the end faces of the Nda rod are ground, polished and silvered to act as an optical resonator. As you can see over here, M1 and M2 are the two reflectors. Okay, so this forms a combination of an optical resonator. One of them is a partial reflector and one of them is a 100% reflector. Now, Nda rod is kept, Nda rod and krypton flash lamp are enclosed inside an ellipsoidal reflector in order to make the entire flash radiation to get focused on the Nda rod. So this is all about the construction of Nda laser. Now we shall move on to the working of Nda laser. So over here, as you can see, here is a ground level, that is E0. E0 is the ground level, ground energy level. Okay. Now, when the flash lamp is on, okay, so when the flash lamp is switched on, optical pumping excites the Nd3 plus ion. Whatever the Nd3 plus positive ions are there, this flash lamp will excite them from the ground energy state E0 to the higher energy level E3 and E4 by absorbing the radiation of the wavelengths of about 0.8 micrometer and 0.73 micrometers respectively. So for E3, to transmit from ground level to E3 energy level, it will absorb the wavelength of 0.80 micrometers, and to transmit from E0 to E4, it will absorb 0.73 micrometers of wavelength, as you can see in the figure. Now, over here, as you can see, is a non-radiative transition takes place and a population inversion takes place. Okay, so upon continuous excitation, population inversion of Nd3 plus ions is achieved at the metastable state E2. As you can see over here, okay, so from E3 and E4 a non-radiative transition takes place and population inversion is achieved at the metastable state E2. So thereafter, any of the spontaneously emitted photon will make the excited Nd3 plus ions to undergo a transition between E2 and E1. Okay, state. Thus, during this transition, the stimulated photon is generated and a laser output is obtained. As you can see over here, the output of laser is shown by the red line, okay, and which takes place of about 1.064 micrometers of wavelength. So that's all for the Nda laser. See you next session. Thanks for watching.